Hey everyone, welcome back. So glad you're here. Today we're going to tackle a huge topic, something that pretty much powers our entire digital world, system design.
You ever stop and think, how in the world does a site like Amazon not just explode during the Black Friday rush? Or how does Netflix manage to stream movies to literally millions of people all at once without that spinning wheel of doom? Well, it's not magic. It's the art and science of system design.
The secret isn't one thing. It's a whole set of powerful strategies. And in this explainer, we're going to walk through the big ones. We'll talk about building for resilience, designing for massive growth, mastering how data flows, and finally, we'll get into the critical trade-offs that every single engineer has to face.
All right, let's dive right in. First up, building for resilience. Now, here's the thing. You can't build a system that never fails. That's just a fantasy. The real goal is to design a system that expects to get hit and knows exactly how to get back up, maybe even stronger than before.
And that idea leads us straight to this fundamental promise you make to your users, high availability. It's really just the guarantee that your service will be there for them, whether it's the middle of a workday or 3 a.m. when they suddenly need it. It's all about being reliable all of the time.
So how do we actually build this kind of resilience? Well, we've got a few really clever techniques up our sleeve. Redundancy is simple. You have backups for all your critical parts, so if one goes down, another one is ready to take its place. Failover is the system's ability to switch to those backups automatically, so fast that nobody even notices. Circuit breakers? They're like the safety switches in your house. They stop a small problem in one part of your system from causing a total meltdown. And then there's chaos engineering, which is as cool as it sounds. You literally try to break your own system on purpose to find the weak spots before they become real-world problems. So the key takeaway here, and this is so important, is this huge shift in mindset. You don't build a great system by just crossing your fingers and hoping for the best. You build an amazing system by planning for the absolute worst. That's what separates the fragile from the resilient.
Okay, so our system is tough, it's resilient, but now what? How do we make it grow? How do we go from serving 100 users to 1 million, or even 1 billion? This brings us right to our second pillar, the engine for infinite growth.
And the magic word here, the one you'll hear all the time, is scalability. And it's not just about getting bigger, it's about getting bigger smarter. A truly scalable system can handle exponential growth without costing a fortune or becoming an absolute nightmare to manage.
And there are really two main ways to think about scaling, and the analogy here is perfect. Vertical scaling, or scaling up, is like giving your one grocery store cashier superpowers, a faster scanner maybe. It helps, sure, but they can still only handle one person at a time. Horizontal scaling, or scaling out, is like opening up more checkout lanes. You can just keep adding more and more lanes to keep the lines moving smoothly. For massive internet scale systems, this is almost always the way to go.
But just being big isn't enough, right? A scalable system also has to be fast, and for that, we have a whole bag of tricks. Caching is like keeping the most popular items right at the front of the store so people can grab them quickly. Asynchronous processing lets you take a big slow task, like processing a video you just uploaded, and do it in the background so the user doesn't have to sit there and wait. Load balancers are the traffic cops of the internet, directing requests to make sure no single server gets totally overwhelmed. And database sharding? That's like taking a giant single phone book and splitting it into smaller lettered volumes, so finding what you need is way, way faster.
All right, so we've built a system that's strong and fast. But, if all its different parts can't talk to each other effectively, it's basically just a bunch of powerful machines sitting in a room doing nothing. And that leads us to our third pillar, mastering the flow of data.
So first, let's talk about how we actually organize all that data. And it's this classic balancing act. On one hand, you can keep your data super organized and tidy to avoid repeating yourself. That's called normalization. Or you can make a few copies and spread things out a bit, which makes it much, much faster to read the data when you need it. That's denormalization. There's no single right answer here. It always depends on what you're trying to build.
Okay, so the data's organized. Next up, how do the different parts of our system actually talk to each other? Well, synchronous communication is basically like a phone call. You ask a question and you wait on the line for an answer. It's direct, but it can create bottlenecks if you're waiting a long time. Asynchronous communication is more like sending an email. You send your message and then you move on with your day, trusting you'll get a reply later. For complex systems, this is way more resilient and scalable.
So, as you're probably starting to see, system design is just this series of choices. There's really no one-size-fits-all solution. And that brings us to our final and honestly the most fundamental concept of all, the great trade-off.
When you're building a system that's spread out across a bunch of different machines, a distributed system, you run into this hard, unavoidable truth. You just can't have it all. You have to make a choice. And this choice is captured perfectly by one powerful idea, the CAP theorem.
Okay, so what is CAP? Well, it's an acronym for three things you really want in a system. C is for consistency. That means everyone sees the same, most up-to-the-minute data. A is for availability. That means the system is always online and ready to respond. And P is for partition tolerance, which means the system keeps working even if parts of it can't talk to each other because of a network failure. But here's the catch. In any real-world distributed system, network failures are a given. You have to have partition tolerance. So your real choice is between C and A. Do you want the most perfectly accurate, consistent data? Or do you want a system that's always available, even if the data might be a tiny bit out of date? You can't guarantee both at the same time.
And really, this is the tightrope every single system designer has to walk. It's not just about the CAP theorem. It's about balancing this whole host of competing priorities. You've got speed, security, cost, and a dozen other things to think about. Great design isn't about finding some mythical perfect solution. It's about making the smartest possible compromises for your specific situation. Now, to help make these tough choices a little easier, we put together this handy cheat sheet for you. Think of it as your playbook for system design. You've got a ton of traffic coming your way? Go with horizontal scaling. Need to speed things up for users around the globe? Caching and CDNs are going to be your best friends. This is really your starting point for matching the right tool to the right job.
So, if there's one thing you take away from all this, it's that system design is the art of the trade-off. There are no magic bullets, just smart, informed choices for very specific problems. And that gets me thinking, and I'd love to know what you think. What do you feel is the most critical strategy for the systems that you build, or even just the ones you use every single day? Hey, thank you so much for watching this explainer. We'd love to hear your thoughts in the comments below. And of course, don't forget to subscribe so you don't miss our next deep dive into these kinds of topics.